And we're back. Okay, Physics 150 discussions on YouTube. So here we have a problem. A long cylindrical conductor of radius r carries a current I as shown in the figure. I've redrawn it right below that so I could mess around with it. This is somewhat... part A is to find the magnetic field when we consider radii within the cylinder, and then part B is find the magnetic field when the radius is outside of it. Now, when you go outside of it, let me just give a quick preview. You fully expect the result to be similar in essence to just the magnetic field due to a long straight wire. We've already accomplished this. The difference is that you have to compute the actual current that's enclosed in the wire, and that's given by the current density. So you have to mess around with some stuff and do some integrations. But once you find what that charge enclosed is, the distance as the behavior as a function of the radius outside of the wire should be exactly like what we've already seen. That is 1 over the radius. So part B is mostly just different in that you have to do an integration that you haven't had to do previously, but the behavior as a function of the distance outside the center of the wire is going to be exactly the same. That is 1 over r. Part A is a little bit less intuitive. You might not know exactly what the behavior of the magnetic field should be as a function of R1, which is less than the radius of the cylinder. Okay, but we're going to start with that one. Let's sort of just move down a little bit. So in general, in a problem like this, we are going to want to use not the law of Biot-Savart. Now, the law of Biot-Savart is obviously always correct with magnetostatics, that is, with problems. Either way, the Biot-Savart law is always correct, but it's got all of those cross products. It's sometimes very hairy to mess around with. If you've got a object with sufficient amount of symmetry, then it's always good to use Ampere's law if you can. It's a little bit simpler to manage. This is sort of like the analogy where in electrostatics with the electric field, you can always start with the infinitesimal form of Coulomb's law and integrate along the charge surface, and you could get the electric field that way. But if you can use Gauss's law because there's sufficient symmetry, then that's always a good way to go. Now, when you're dealing with Ampere's law, I just want to write down the general form is that you have an integral over some loop, call it C, and B dot dl is equal to mu naught I enclosed by that loop. So in this problem, all of the tricky stuff is going to be a function of the fact that figuring out what I enclosed is going to require some more work than usual. A lot of times we just give you that. In this particular case, that's not going to be given. So dealing with part A, where R1 is less than the radius of the cylinder, let's draw the front of this just to give us some idea of what's going on. Okay, so this is the center, the total radius is r, but we are interested in the radius r1. So let's deal with r1 like this, and that's going to be less than the radius r. So just draw a circle like that. We are interested in what is the magnetic field at that circle. Now what we can do is we can use Ampere's law, and let's call this loop C1, and we're doing Ampere's law is going to be the loop around C1, B dot dl. Okay, so what is B and what is DL? So in this case, let's imagine that we are going around this circle in a counterclockwise fashion. We've got that DL is going to be pointing like this. And if the current is coming out of the page like this, let's say that the B field is also going around like so. Essentially what that means is that the B field and DL are both aligned with each other. So that the dot product is just going to be BDL. And one thing is that what we call C1 is called an Amperian loop. And oftentimes, the way that you want to choose your Amperian loop is, if you remember from Gauss's law, you want to choose your Gaussian surface so that the electric field is constant all along it. Same thing here with the Amperian loop. If you draw a circle around the center, there's no reason why the B field at one point on the circle should be different than the B field on another, because there's a sort of cylindrical symmetry here. There's nothing different about this point as opposed to another point or another point. So what we say is that the B field is constant along that loop, so you can bring it out of the integral. DL. And so now we're just dealing with an integral along a circle. So what is the length along a circle? Well, that's just B times 2 pi r1, the circumference. So now let's rewrite Ampere's law. This is B times 2 pi r1 is equal to mu naught times the I enclosed. What does that mean? We could solve for B. B is equal to mu naught I enclosed over 2 pi r1. We could solve for B if only we knew what I enclosed was. So now let's find I enclosed. Now, I enclosed, the way that we want to find out what this is let's consider a little segment of this wire. Let's consider a segment that's like a thin sort of shell, like that. What is the amount of current that flows through that shell? Well, what we know is that some infinitesimal piece of that wire is going to be equal to the current density times the area of that shell. We know that J, the current density, this is given to us, is equal to 3B times, so this is a current density that changes the further you get away from the center. So this is r to the third. It's just some random function picked out of thin air, it looks like to me. I don't know what the physical motivation is for this. It just looks like, okay, pick some function. Now what is dA? dA we usually write as being dx dy. That's not going to be the most convenient thing, because here we see that the j is written in polar coordinates. So when you switch to polar coordinates, r and theta, the area element dA is written as r dr d theta. So that is the area of one of those circular sort of shells that I drew. So if I want to find, oops, no, we don't want to do that. Yes. So if we want to find the current going through one of those shells, we write what j is. This is 3b r cubed times what dA is, which is r dr d theta. We can simplify this because the r's are the same r's, so they multiply each other. So you have 3b r to the fourth dr d theta. Now, if I want to find the total charge enclosed up to a radius r1, so let's just go up for a second. We want to find the total charge that's enclosed in this area here. So we are going to integrate from the origin all the way out to there. Because some little amount of charge is going to be given by dI in this form. This is some little amount. And if I want to find the total amount of current, then I'm going to want to integrate that. So I enclosed is equal to integral dI, which in this case is going to be, if I want to do an area integral, I integrate around the entire thing, around the entire cylinder, because there's current everywhere there, so 0 to 2 pi. I also integrate from 0 to r1, where r1 is less than capital R, and then I plug in the integrand, which is 3b r to the fourth dr d theta. Okay, now we want to make this simpler to solve. Let's bring the constants out. That's 3b. Let's give everything that's next to an r. Let's bring all the integrals into the appropriate integrations. So this is r to the fourth dr. And there's no harm in going from 0 to 2 pi times, oops, giving away the game right there. This is d theta. Now we can easily compute that d theta because the integral of d something is just that something. And this is going to just integrate to theta evaluated from 0 to 2 pi. So this is just going to go to 2 pi. So this is equal to 6 pi b integral from 0 to r1 of r to the fourth dr. Now, here, what we're going to want to do is use the fact that integral of x to the n dx, so this is an indefinite integral, is equal to x to the n plus 1 over n plus 1 plus an integration constant. The reason that you do that is because if you take a derivative with respect to x to the n plus 1, then this is n plus 1 times x to the n. So clearly, if you take a derivative of this answer, you get back x to the n. That's why it works. So we're going to use that fact so that integral from 0 to r1 of r to the fourth dr, which is the integral that we have left over. This is r to the fifth over 5 from 0 to r1. This is just r1 to the fifth power over 5. And we're going to use that integral later again, so that we are left with I enclosed is equal to 6 pi b r1 to the fifth power all over 5. Let's make sure that that's correct. Yes, looks like it's okay. So that's our I enclosed. And then we had that B was equal to mu naught I enclosed over 2 pi r1. Plugging in what we had for I enclosed, you're going to have some factors cancel. For example, an r1 is going to cancel with the r1 to the fifth. You have a 2 pi that cancels, and then you're going to end up with 3/5 mu naught times b, the constant that was given, times r1 to the 4th. So let's rewrite that just to make it look better. 3/5 mu naught b r1 to the 4th. And what you see here is that as you move further away, now the current density is increasing as you go further away. That's what that function that was given means. So that as you move further away from the center of the cylinder, you enclose more and more charge. Therefore, the B field is actually growing. If you wanted to plot this, it's essentially growing with r to the 4th power. So this is r, this is b, and you've got something that's growing like r to the 4th until it reaches the value r, in which it reaches its maximum value. So actually, this is a good segue, because what we know also is that, so now we're looking at part B. If you've got a long straight wire, so we've seen this before with some current I, and you are some distance, say, just for consistency, R2 away, we've calculated before that the B field goes like mu naught I over 2 pi R2. So if you had to draw a function of that thing, it looks something like this is R2. Now in this case, the wire that we're considering, basically this is the distance from the center of it. So just to make it relevant to our problem, we can also just, this thing could have some size like this. And let's call that R. The point is that after the point R, the B field is going to go down like 1 over R2 from its maximum value. Something like this. So if you piece together the two functions, you're going to find that it looks something like it goes up and then it drops back down. Now the R2, this side of things should actually decay slower than this side goes like R to the 4th, and this is like 1 over R. So the left-hand side of this should certainly be a steeper increase, but I didn't draw it correctly. So just keep that in mind. So you have that the B field keeps growing inside of the cylinder up until you get to the maximum value, and then it decreases as you get further away, which kind of makes some amount of sense. Okay, so let's actually show how that works. Now for part B, we're dealing with R2, which is greater than R. So we are dealing with, this is the front of the cylinder, this is the radius R, and we want to find out what is the B field at some radius R2 when R2 is greater than R. And let's call this loop here, let's call this C2. We want to find the B field out here. So we're going to use Ampere's law. So integral of B dot dl over this times C2 is equal to mu naught I enclosed. Again, we're going to have to figure out what I enclosed is. It's going to be the total charge this time that's enclosed by this wire. Before, we only considered the charge enclosed by a subsection of it. Now it's going to be the entire thing because we're dealing with a magnetic field that's outside the wire. Now, dealing with the left-hand side of Ampere's law, we just did an example of this. This ends up going to 2 pi r2 times b. So through the exact same steps that we took before, you could just do 2 pi r2 times b equals mu naught I enclosed. Now, again, we want to find I enclosed. We are dealing with, we want to, first, if you want to find what I enclosed is, and it's not, and the current is not uniform, or the charge density, or the current density is not uniform, you need to know that the current density times dA gives you one increment of the charge. That is, you've got the front of this thing, this is the center, and dI is the amount of charge. So just take like a little and just to make this. So you see that this shell is going to have some width dr, and it's also going to have, rather, it's going to have some thickness dr, and it's going to go through some angle d theta. So maybe this was not the right way to draw this. Sorry. What you have is a little segment here with also going through a range d theta. So this is your little dA right there. And you want to add up over all such dAs. So you add up this one and this one. That's why you have to go around with theta. And then you have to do that for each radius. So then you have to move out slowly but surely. So that's where that integration measure comes from. You want to add up over all of these little segments. So we go back to dI is equal to b3b r to the third times r dr d theta. And this is 3b r to the fourth dr d theta. Perfect. Okay, so we're going to go through a lot of the same steps. I'm going to just sort of skip this a little bit. I enclosed, you get, so I'll just at least write out the full integral. You're going to want to integrate from 0 to 2 pi again. That part makes some sense. And this time, to get the total current that's in the wire, you're going to integrate from 0 to r. That's the important part. From 0 to r, and it's going to be the same integrand, 3b r to the fourth dr d theta. Now, the theta part gets integrated pretty easily, and then we end up with the prefactor that we had before, 6 pi b integral, this time from 0 to r of r to the fourth dr. Okay, so we can compute this integral the same as we did before. This is going to be r to the fifth over 5 evaluated from 0 to r this time, which is just capital R to the fifth over 5. So let's just skip to that. We have that I enclosed equals 6 pi b r to the fifth over 5. So that's the total charge that's enclosed, and this is a constant because R is a constant, B is a constant. All of these factors are constants. Once you get outside of the cylinder, this is the total charge that's running through that wire. So now, if you want to find B, this is going to be equal to mu. Well, actually, we didn't write this out completely. So let's start with that. You had 2 pi R2, B equals mu naught I, or that B is equal to, and this is enclosed, mu naught I enclosed over 2 pi times R2. So the behavior of this B as a function of R2, the distance outside of the wire, is going to be 1 over R2 because I enclosed does not depend on R2 at all. Remember in part A, B was a function, increasing function of R1. Here it decreases with increasing R2. If I write this in terms of all of the parameters given, then what I have is B is equal to, some of these factors cancel, so that I am left with 3B mu naught R to the 5th over 5. That's one factor. And then the behavior like outside is given by 1 over R2. So this is what I was talking about before. When you have a function of the magnetic field with the distance outside, R, and this is the strength of the magnetic field, it goes up like R to the 4th, and then it decreases at a much slower rate, where this connection period, this is the radius R. So this is like R to the 4th. This is like 1 over R. Okay, so I hope that that was helpful. I'll see you guys around.